In Chapter 1, we learned how to find the first derivative. In Chapter 2, we are going to learn about the implications and the applications of the first derivative. So first off, as a quick reminder, the first derivative, f prime of x, this is equal to the slope of the tangent line at the point x equals to a. So let's take a look at what's happening. If the slope at this point of the tangent line is negative, this is happening because the graph is decreasing. Okay, once again, if you have a negative slope, it's because the graph is decreasing. If at a point the slope of the tangent line is positive, it's positive because the graph is increasing. So one of the important applications of the derivative is that when the tangent line has a negative slope, the function is decreasing at that point. When the tangent line has a positive slope, the function is increasing at that point. In other words, we have a theorem that if f prime of x, which once again, the first derivative is the slope of the tangent line at the point x equals a, is greater than 0 for all x in an interval, then f is increasing over that interval. If the derivative is less than 0, then the function is decreasing over that interval. Because remember, if the derivative is positive, it means the slope of our tangent line is positive, so the function is increasing. If the derivative is negative, then the slope of the tangent line at that point is negative, so the function is decreasing. Later on, we will talk about what happens if f prime of x is equal to 0. Now, how is this useful? If this represents a profit function, we can take any production level. So let's say we're producing x units, and this is our profit. Even though our profit is positive, we can say that at that point our profit is decreasing. At this point, whatever our production level is, if this is our profit, then at that point we can say our profit is increasing, which is good. Increasing profit is good, decreasing profit is not so good. Now, we're going to talk about the critical value, which will be an important topic in this chapter. So here's a definition. A critical value of a function f is any number c in the domain of f for which the tangent line is horizontal or for which the derivative does not exist. Okay, so the critical value can be found in two different ways. One is if f prime of x is equal to 0. If the derivative is 0, then the slope of the tangent line is 0. So this is what it looks like. Basically, a critical point is either a relative maximum or a relative minimum, because at those points, the graph is peaking, so the slope of the tangent line is going to be 0. So when the first derivative, or the slope of the tangent line, is equal to 0, we get a critical value. We also get a critical value when f prime of x is undefined. And this usually happens, we get an undefined f prime of x whenever we are dividing by 0. Okay, so whenever, and I'm going to keep coming back to this over and over again. The critical value occurs two different ways. One, if the derivative is equal to 0, and two, if the derivative is undefined. If the derivative is undefined, kind of looks like that. Here's an example. Let's find the critical values of the function f of x equals 2x cubed minus 24x squared plus 72x minus 10. And we're going to verify by graphing this on to Desmos. So first of all, when you see the term critical value, we think about these two conditions, that the derivative has to be 0 or the derivative has to be undefined. In either case, we need to know what the derivative is. So start associating critical value with the first derivative. So we're going to say that f prime of x is equal to 3 times 2, which is 6x to the second power. 2 times 24, that's going to be negative 48x. And then, sorry, here it's going to be just plus 72. That's going to be the first derivative. Now, in order to find the critical values, we have to set the first derivative equal to 0 or see when is the first derivative undefined. The first derivative is undefined only if you're dividing by 0. So let me write that down. F of x is undefined only when dividing by 0, which basically means we need a variable on the denominator, which we don't have. If there's no variable on the denominator, then we can't divide by 0. So this cannot have an undefined value. So let's just take our first derivative, which is 6x squared minus 48x plus 72, and let's set it equal to 0. Now we can either factor this, we can use a quadratic formula, or we can graph it. But before we do any of that, let's make this a little bit more simple. They all have a common factor of 6, so let's divide both sides by 6. And this will give us x squared minus 8x plus 12 is equal to 0. If we factor this, we're going to get x minus 6 times x minus 2 is equal to 0, which means x equals to 6 or x equals to 2. So our critical values are going to be x equals 6 or x equals 2. So at x equals 6 or x equals 2, the slope of the tangent line will equal to 0. All right, and let's verify this by graphing it on Desmos. So let me go to Desmos real quick. Okay, and here's our function. Our function is f of x equals to 2x to the third minus 24x to the second plus 72x minus 10. Okay, I'm going to zoom out a little bit and look what's happening at when x equals to 6. When x equals to 6, the slope of the tangent line is going to be 0 because we get a horizontal tangent line. And also at x equals to 2, look at what's happening. The tangent line is going to be horizontal, which means we will have a slope of 0. Okay, so those are our two critical values. Okay, let's consider the function f of x equals to negative 2x cubed plus 45x squared minus 300x plus 8. So first, let's find the critical values. Okay, once again, critical values, either f prime of x has to equal to 0 or f prime of x is undefined. I'm going to keep saying this over and over again so it just stays fresh in your minds. Either way, we need f prime of x. So f prime of x, 3 times negative 2 is negative 6x squared. 2 times 45 is going to be 90x. Then we have negative 300. That's going to be f prime of x. This can't be undefined because we don't have any kind of division by 0. We're not dividing by a variable. So we can take the first derivative and set it equal to 0. Once again, your options are factoring, quadratic formula, or graphing. Before you do anything, just reduce this or make it a more simple equation. So we divide it all by negative 6. The reason we divide by negative 6 is so the x squared could be positive. So we're going to get x squared minus 15x plus 50 is equal to 0. And then if you factor this, we're going to get x minus 10 times x minus 5 is equal to 0. So we get x equals 10 or x equals 5. So these are the two critical values. Now look what's happening at the critical values. At the critical values, if you go back, the function goes from being increasing to decreasing, or it goes from being decreasing to increasing. That's why the critical values are critical or important, because at these values, the function changes directions. So the next part says, on which intervals is f of x increasing, and on which intervals is it decreasing? So on one side of the critical value, the function will be increasing. On the other side, it'll be decreasing. So we got to figure out where is it increasing and decreasing. And we're going to use the following rule. If the first derivative is greater than 0, then the function is increasing. If the first derivative is less than 0, then the function is decreasing. So anytime you're asked to determine when the function is increasing and decreasing, we're always going to be looking at the first derivative. And this is another thing I'm going to say over and over again. Anytime you want to see when the function is increasing or decreasing, we are going to be looking at the first derivative. So here's how I want you to set this up. First of all, we're going to make a number line. And we're going to, on the number line, we're going to put the critical values, which are 5 and 10. And I'm going to split this up into different intervals. Because remember, on one side of the critical value, the function is decreasing. On the other side, it's increasing. So we want to figure out, on this side of 5, the left side, is it decreasing or increasing? On the right side of 5, is it decreasing or increasing? On the right side of 10, is it decreasing or increasing? So first thing we do is we're going to put in the interval. So this is negative infinity, this is infinity. So the first interval is from negative infinity to 5. The second interval is from 5 to 10. The third interval is from 10 to infinity. And we always use parentheses because remember, for increasing and decreasing, we don't include the endpoints, because at the endpoints, the slope is equal to 0. So we're not going to include those. Now, we pick a test point in each of the intervals. So the next thing, we need to pick a test point. So this is 5 going towards negative infinity, so any number less than 5 will work. So we can just pick x equals to 4. Between 5 and 10, we can pick any point. I'm going to pick x equals to 8. And to the right of 10, we can pick any point. I'm going to pick x equals to 11. Okay, that's going to be our test point. Now, what are we testing? We're not testing the original function. We are testing the derivative, because if the derivative is greater than 0, then it's increasing. If the derivative is less than 0, then it's decreasing. So anytime you want increasing or decreasing, we're looking at the derivative. So the next step is we want to find out what is the value of f prime of x for whatever x we're testing. So we want to find f prime of 4, we want to find f prime of 8, and we want to find f prime of 11. We want to find the value of the derivative at these x-axes. Okay, so this is our derivative right here. Use this one and not the simple. So we simplified it just to solve the equation, but this is the actual first derivative, so we're going to use that. Now, I highly recommend that you don't do this by hand. You can use Desmos or like a calculator or something that's going to make it easy on you, but I'm going to be using Desmos. So here's my first derivative. It's equal to negative 6x to the second power plus 90x minus 300. I put in the function, and I want to evaluate the following. I want to evaluate f of 4, I want to evaluate f of 8, and I want to evaluate f of 11. So I have negative 36, 36, and 36. And remember, this represents the first derivative. So let me put those in. So f prime of 4, the first derivative of 4, this is equal to negative 36. This is equal to positive 36. This is equal to negative 36. So because the first derivative, which is a slope at 4, is negative, then here's what's happening. The slope of the tangent line is negative, which means the function is going to be decreasing. Here, the slope of the tangent line at x equals 8 is positive, which means the function is increasing. Here, the slope of the tangent line is negative, so because the slope of the tangent line is negative, once again, the function is decreasing. So now we make a conclusion about the original function f of x. Okay, so since the first derivative is negative, the function is decreasing over the first interval. Since f prime of 8, the first derivative is positive, the function is increasing over this interval. And over here, the function is decreasing. Okay, decreasing, increasing, decreasing. So the function is decreasing over the intervals negative infinity, comma 5, union 10, comma infinity. And the function is increasing over the interval 5, comma 10. And we will do this in class. We'll graph this in class to verify the information. So I'll write a note on the side to graph this in class.